Hello, everyone, and thank you for joining our presentation for today. I am Hussam Alisa from Microsoft Data Center Advanced Development Team, along with my co-presenters.
I'm Robert Langston from Microsoft's Cloud Hardware Engineering Team.
And Brandon Rubenstein, the Director of Mechanical Engineering for Microsoft's Cloud Engineering Team.
Today, we will be giving an update on liquid cooling enablement for the Olympus rack using liquid-to-air rear door heat exchanger assist. One of the main objectives of OCP Advanced Cooling Solution work streams aims to streamline and standardize liquid cooling technologies. This session will be focused on cold plate enablement using air assist, with focus on enablement of liquid cooling in air-cooled dedicated and air-cooled optimized data centers. So what's driving the industry to liquid cooling or to require cold plates for their chipset? So what we're seeing is an increased chip fluxes, whether it's CPUs and GPUs and accelerators in general. The chart to the upper left shows CPU power and T-case requirement for different CPU generations. The blue column represents power, and the orange represents T-case required. We can see that across CPU generations, power is increasing. Could be number of cores increasing, or other features are added to the chip. Similarly, looking at the GPU charts, power has been going up constantly. And sometimes it is possible to have the power increase accompanied with a reduction in the required T-case due to power increase or die size shrinking, etc., which makes the thermal solution more challenging. There has been a lot of work, though, and an investment into optimizing air-cooled data centers. So as we move from chiller-cooled DCs with higher mechanical overhead to introducing economizer data center and free air-cooled data center, PUE has been going down, as well as water consumption, as well as cost. So this shows that there has been a lot of effort into optimizing air-cooled data center on the mega scale. But in the light of the fact that most of current hyperscale data center have been optimized to run efficiently using air-cooled, and when we require to apply liquid cooling into them, we have to be cognizant of the fact that not all the applications might require those higher flux chips for liquid cooling. And we might end up with mixed low flux and high flux chips based on racks throughout the facility. So we need to make sensible TCO-driven decisions. Do we need water throughout the data center or locally, which could be retrofits that can be rather costly or disruptive, or what we will be showing you here today, which is the use of air assist water cooling. In the next couple of slides, we will share some case studies we ran on compute and GPUs using liquid cooling. Here we are showing a case study on the Olympus compute server. As you can see, the conversion of the air-cooled Olympus server to a hybrid cooled or a cold plate-based liquid cooled server is pretty seamless, which involves fans removed, tubing added. The fan speed will auto-modulate, reducing the server power. And this shows that we can do a rather quick enablement for higher chip flux that might prove to be challenging to air cool. The chart to the left shows a comparison between CPU temperature running air cooling at 35 Celsius inlet versus cold plates across a sweep of water temperatures. The gray bars show the air-cooled CPU junction temperature versus the colored bars showing liquid-cooled CPUs across a sweep of ASHRAE W1 to W4. The uber point here is that the use of liquid cooling enables us to make decisions such as run with colder water temperatures, potential to take a hit on efficiency, but an enabler for further chip performance. So there's a trade-off to be made here. Another option would be to run warmer water, enable infrastructure efficiency gains such as dry coolers, etc., and still potentially run colder than a case of air-cooled solution. One thing to point out, though, in this slide that there was, as you can see, there are cold plate or liquid-cooled modules almost on most of the components, CPUs, DMF, M.2s, and FPGAs. And this affects the heat pickup ratio between the air and the liquid. But in reality, that decision has also to be TCO driven, taking into account the power reduction because the fan's ramping down further. However, we need to take into account the effect of the added cost for the extra modules. This is another case study we ran on our Olympus expansion chassis, HGX1, which is a server with 8 GPUs. The air-cooled chassis was running using 3 UTOL heatsink solution, while the liquid-cooled has been retrofitted with 8 cold plates. This study was a collaboration across the server, software, hardware, and GPU teams, as well as externally with CoolIT, ZT Systems, and Ingrace Systems. Similar to the CPU case, so we ran an investigation whilst running neural network type workloads provided by Microsoft GPU team. In both charts, light blue and yellow columns represent the air-cooled permutations for cases of 35 Celsius and 25 Celsius air respectively. Orange, dark blue, and gray bars show data points for the water temperature sweep. The server power consumption graph shows that the effect of reduced server power when using liquid cooling due significant fan speed reduction and reduced leakage current. While the average GPU performance chart showed an increase of performance with colder temperature. Again, this brings up the decision that liquid cooling enables, which is running colder or warmer water and taking into account the trade-off of infrastructure versus chip performance. Okay, so the previous examples were case studies on retrofits, meaning air-cooled servers and chips transformed into liquid cooling for sensitivity analysis. But such studies encourage building chips that are higher power or higher performance and requires liquid cooling from the get-go. So the big question we are trying to address here, how can we enable liquid cooling for higher flux chips in data centers that where facility water is not present? In the session titled Air-Assisted Liquid Cooling, Cold Plate Enablement in Air-Cooled Facilities, air-assisted liquid cooling options were discussed. Here we will have a deeper dive into the Olympus rear door heat exchanger system. As you can see in the leftmost figure, that shows the Olympus rack with a rear door heat exchanger and N+1 fan configuration. Looking inside the rack with the rear door heat exchanger open and the rack empty of servers, you can see the Olympus rack PMDU for blind mate power, but you can also see the right blind mate manifold for blind mate cooling. Ease of services is an important aspect as well, as you can see in the right and the clip to the rightmost, where enabling blind mate power and cooling in play facilitates serviceability. Next, Robert will walk you through details of the Olympus rear door heat exchanger system.
As Sam mentioned, the goal behind the air-assisted liquid-cooled rack is to provide an open-loop liquid cooling levels of performance in an air-cooled data center in order to enable higher heat flux chips. This is accomplished by using a rack-sized heat exchanger and centralized pumping system to maximize performance and efficiency. The liquid heat pickup ratio can vary depending on server design, where certain percentages of the heat is circulated through the liquid loop to the rear door heat exchanger where the remaining server heat is picked up by the air flowing through the server in a more traditional air-cooled fashion. Ultimately, 100% of the server heat is rejected into the facility air. The solution is being designed to cool up to 40 kilowatt rack with less than 5% cooling overhead and an airflow consumption of less than 145 CFM per kilowatt. It's intended to be both Olympus rack and ORV3 compatible. The rear door heat exchanger is designed to fit the 48U Olympus rack and be compatible with the OCP rear door specification. It uses 5 hot swappable 280 millimeter axial fans capable of up to 4,800 CFM. There's a mounting bracket which provides the interface between the door and the rack and allows for easy replacement of the rear door if needed. This mounting bracket can be changed to allow for compatibility with either the Olympus rack or the open rack. The current POC system has a standalone control system for the door. However, future iterations should interface with the pumping unit to allow for external control and management of fans. Telemetry from the door includes differential pressure, air inlet, and individual fan, tack, and control signals. The fluid distribution manifold is designed to mount on the rear of the Olympus rack and provide a blind mate interface for up to 42 1U Olympus servers. It uses Stobleed CGD03 blind mate connectors to the servers and CGB20 manual mate dry brake connections for the inlet and outlet fluid. It also incorporates an automatic air bleed valve. In the future, the manifold and quick disconnects could be modified based on server requirements. For example, to support servers of different U heights. Additionally, it could be converted to use standardized quick disconnects once available. Microsoft and Facebook have been collaborating on a common specification for the reservoir and pumping unit. The specification is discussed in greater detail in the air-assisted liquid cooling, cold plate enablement, and air-cooled facilities thread. But it is intended to be compatible with both Olympus and open rack designs and can support various methods of air-assisted liquid cooling. The design uses redundant custom GRI pumps with maximum one pump performance of 50 liters per minute at 25 PSI. The pumps are fixed in the current POC, but we are driving for hot swappability in future iterations. The system can monitor supply and return pressures and temperature, as well as flow rate and pump speed. The RPU will interface with the rear door heat exchanger to manage and monitor its differential pressure and fan speed as well. The internal control system will vary pump and rear door fan speeds to maintain defined operating conditions such as flow rate and temperature. It will also interface with a rack level management system to allow for external monitoring and adjustment of operating conditions. The control system in the RPU will allow for the liquid cooling system to be used across a broad range of platforms and use cases. Operating conditions can be adjusted for each platform to allow for optimal system performance. For example, here we show how two 40 kilowatt racks with varying heat pickup ratios can be adjusted for either efficient operation or to maximize cooling performance. By increasing the supply water temperature by about 4 degrees C, the required rack airflow rate and cooling power overhead can be greatly reduced. Although there's still a lot of testing to be done in this initial POC, there are several improvements and optimizations that we would like to drive into future iterations of the design. We need to implement hot swappable pumps in the RPU to improve service and minimize service downtime. We need to develop the control systems for the RPU to manage pumps and fans and external communication paths for monitoring and management. We think there may be opportunity to optimize door coils and fans to improve performance and minimize the impact of fan failures. Finally, we need to identify multiple sources of pumps that meet the RPU requirements to ensure supply chain integrity.
So thanks, guys, for all the excellent work that went into the presentation and all the work that went into the investigations. I think the big overarching message here is that we're committed to the liquid cooling solution in an open platform, but we need assistance. So this slide is dedicated to some of those concerns. So in order to develop at the scale and the cost that we need standardization of specification and interfaces. So all the components need to be standardized. They need to fit together. They need to be somewhat commoditized: rear door heat exchanger, manifold, RPUs, pumps, and coolants. We need consistent guidelines for deployment, serviceability, and control, so that different sources have uniform means of upkeep and deployment for these systems. Vendor and end user collaboration on monitoring is a key to integration into the overall platform and infrastructure. So without that, it really is a custom solution, even if the hardware looks identical, and again adds to the difficulty in scale deployment. And finally, leakage and risk mitigation needs to be standardized, again, for the standardized interface into the infrastructure to minimize the effort of scale deployment. So to close out, thank you for watching and listening to our presentation.
Okay, thank you everyone. I think we got some questions. Please feel free to type in your questions in the chat window or in the questions and answers. That's fine too. We had one question about will liquid cooling lead to lower IT power? Well, the answer is yes. We had another question about CPU power consumption for the Olympus server. The example we showed was at 200 watts, but the power value can vary depending on the SKU. And Robert, I think there was a rear door heat exchanger question at the end.
Yeah, there's a question about what happens if one of the rear door fans fail. So the system will be monitoring fans, and so if we do see a fan failure, that should trigger a service event for somebody to come replace the fan. This is honestly one of the things that we're trying to do some more analysis on in the POC and see what the performance impact is when a fan fails in that time before somebody can service it. We've done some simulation, and it looked like that we would only see a few degrees temperature rise in the inlet water temperature when one of the fans fails. And we think this is partially because the servers are still have fans on them, and they're helping this continue to drive some airflow through the door. So it's reduced, but it's not entirely. The section of coil that's covered by that fan isn't entirely without flow. So we still get pretty reasonable performance even with the fan fail.
Yeah, so there's a question on uneven pressure in the manifold and servers closer to the bottom getting the higher pressure. So I don't know if, Robert, you want to speak to what we've found in manifold pressure modeling?
Yeah, so we've sized the manifold and the quick disconnect, so there's very little flow differential from across servers that are plugged into the manifold. The QDs just in general have a fairly high pressure drop, and so that helps kind of even out the flow in the manifold. But we have done quite a bit of analysis there, flow analysis on the manifold to make sure that we don't get uneven flow up and down the manifold. The it's of course assuming a uniform server load on there, so we might have to reevaluate if we were plugging in servers with different resistances or different kinds of servers that had different internal resistances to them. But at least with a uniform server load, it looks like the flow should be within, I think, about 5% of the minimum to the maximum in the manifold.
There was a question about the fluid level in the reservoir and the RPU unit and how to maintain that level. So it really is also a question of the initial definition of how many liters or gallon we need per system. And then adding to that, there is some redundancy on the fluid side as well. So there is some extension to the reservoir in the RPU unit.
The other part to that is management. So the entire system needs to monitor itself for health, and there's an entire management infrastructure that we really didn't go into detail on in this presentation that monitors itself for low levels of fluid leakage and that kind of thing.
Right. What water additives are you using, Shlomo Navani? So this is PG25. So water and glycol, and obviously the corrosion inhibitors and some of these additives.
So to the question about VRM temperatures, so the rest of the system is still designed for air cooling. So, this being a hybrid system, we account for the heat being removed by the CPUs or whatever cold plate whatever components are being touched by the cold plate. But the rest of the system is traditionally designed for air cooling. So there is airflow control through the server, just as there would be if it was completely air cooled. And it's designed for, as we would normally do with unmonitored components like a VRM. Well, VRMs are somewhat monitored, I guess, but components that are unmonitored would not be monitored for airflow rate. They would be set at an assumed high power level, and the inlet temperature would drive the flow rate to make sure that those components are kept cool. The monitored components are real-time monitored, and fan speed adjusts to keep them under their temperature limits. Just very traditional airflow control.
Yeah, just to elaborate on that a little bit more, the intention is to still have fans on the server that do the localized management of the air-cooled components on the server. So the rear door will be providing some bulk airflow through the system, but if an non-liquid cooled component on one server starts to get hot, the fans on that server can ramp up to help drive more airflow to cool that component on the server as well.
There's another question by Romeo. Is there any standards you are using for preventive maintenance, particularly for liquid cooling pipes and reservoir? I can make a quick comment, and Brandon and Robert, feel free to jump in. But as of now, we have been working with our partners on the technology and basically using some of the already existing best practices, mostly adapted in liquid cooling supercomputers.
I think kind of similar to one of my previous answers, that this is something that we want to dive into more with the POC testing to see, what kind of maintenance schedule do we have to follow? Do we start to see issues over time? that sort of thing. So we do want to follow best practices that we've seen out in the industry, but we want to see what we can, if there's anything we can improve to take this out to a larger scale, kind of hyperscale level.
So to David's question, if these are designed for non-raised floor deployment only, they're heavy systems. You have a lot of fluid and pumping units in them. I don't know that we've evaluated it for all raised floors, but obviously there's a limitation to the weight that raised floors can handle. So it's not specifically designed out for raised floor, but it is we're going to have to be aware of the weight of the rack and the support that the raised floor can handle. I don't expect there's any airflow reason to be concerned with raised floors.
And there was a question about installation timeline goals. So what we're trying to do here through this presentation, as well as the other presentation we're doing through OCP for liquid cooling, is to try and prep our industry for the advent of the incoming liquid cooling chips, and because they will require liquid cooling. So our effort here is to align with OCP and make the adaptation to liquid cooling more seamless.
I think that's the key thing there, especially to Shlomo's question. Liquid cooling exists. Cold plate liquid cooling is something that's been around for quite a while. The effort that we're going through with OCP is to make liquid cooling scalable at the level that we need it to be scaled. So that's through standardization of interfaces, standardization of materials, and commoditization of a lot of these things that we need at very high volumes and the requisite quality levels. So that's really our main thrust of working through this liquid cooling activity within OCP.
There's a question. Yep, go ahead, Brandon.
Yeah, I think you were going to answer the same one, Sam. The balance on TCO between efficiency and performance. Generally speaking, the way this works is you have a performance spec that you're trying to hit, and you design your cooling solution to meet that requirement. There are different ways to meet that requirement, and you want to take it's a balance, like you said, and you have to figure out what the best cooling solution is to meet that cooling temperature requirement, or power to thermal resistance requirement, I should say, and the best technology that meets that at the lowest cost. Sometimes cold plate is it, sometimes it's not.
Yes, agreed. And to Brandon's point, even so, this is kind of a TCO when we're building infrastructure or in the hardware or on the data center side, but also expanding it to operation. How do we want to operate these liquid cooling system? Because we can have modes where we can adapt liquid cooling, control stuff on the water side and on the air side for the liquid to air exchange, and either have it operate for efficiency, where we maximize the water temperature coming to the chips and minimize the overhead of pumps or fans, or we can do it the opposite way, minimize the water temperature coming into the chip with an overhead increase in the pumps and the power fan, assuming there is a gain out of that, for example, on chip performance.
I think we're trying to design the system to be as flexible as possible so it can take advantage of different kinds of systems. So we're trying to design it with a very high level of performance to make it robust and future-proof for chips that come several years down the line. But with a chip that has lesser cooling requirements, we could obviously turn down the fans and turn down the pumps in order to lower the power consumption of the total system to save in power that way.
Okay, I think we ran out of time here. So thank you, everyone.
Yeah, thanks, folks. Thanks for the great questions and feedback.
Yep, and thank you. And if any more questions come up, feel free to put them into the presentation window, and we can field them as we see them through that chat. Thanks, everyone.